All right, we are going to be continuing our conversation about Heaviside functions. We introduced the step function last lecture and created different functions out of it. We came up with its Laplace transform and worked with it for a few examples. But we still haven't talked about a few details. There are different ways to represent piecewise functions. We can use a traditional sort of piecewise function sort of setup, or we can write it in terms of a sum of these different Heaviside functions. And it's really useful to be able to convert between the two because when you have a differential equation with some sort of switching behavior on the right-hand side, that might be written in terms of a piecewise function. You want a function to follow this sort of behavior for the first part, and then it switches to something else for the second part, for example, after a certain time has passed. So it's really useful to be able to change that piecewise function into Heaviside functions, because that way you can then take Laplace transforms, as we did in the above examples, and work with that instead. So there's a page here in the notes that will help to kind of write one function in one sort of way of expressing these sorts of discontinuous functions or changing behavior functions. To write a piecewise function in terms of a Heaviside function or vice versa. I put together these pages a few years ago because students wanted sort of some directions, but I think that a lot of the time it's really intuitive. Just understanding what those U functions, what those step functions are doing, really helps you interpret how you would do this conversion without really memorizing a way of going forward. But I have some directions here, and it'll work every time. So if you are given a piecewise function, you can write down the function appearing in the first branch, and then for each value a that separates two branches, so at the time that the behavior switches, you add a new function that represents some piece that turns on the new function while at the same time turning off the old behavior. So we're going to see this in this example at the very least. So we have this here. We have f of t equals three different behaviors. So we have 1 if t is less than 2, a negative t if 2 is less than or equal to t is less than 3, and 2t minus e to the t after that. So if I take a look at this, there are 2 times when that behavior switches. At t equals 2, the behavior switches from 1 to minus t. So it was 1, and at that time I want to turn off the 1 and turn on the negative t. That means that I'm going to have to kind of add in the minus t at that time, while at the same time turning off the 1. So I'm going to have to multiply kind of those different things by a particular Heaviside function. And then at t equals 3, things change again from minus t to 2t minus e to the t. So if we follow the directions from the last page, or just use our intuition, if you understand how these functions work, up until t equals 2, the function is just 1. So I'm going to write down a 1. That's how it starts. It's at 2 that things change. And so what I'm going to do is add some sort of changing behavior. U of t minus 2 is the basic step function that turns on at t equals 2. This is a function that is either 0 or 1. The idea is that up until t equals 2, that step function is going to be equal to 2. So I just want, or is going to be equal to 0 rather, and at 2 it's going to change to 1. So this, if we recall from the last lecture, this is equal to 1 only after t equals 2. Okay, so once we get to t equals 2, it's turns on to a 1, but before that it's equal to 0. So but is 0 before. And so anything attached to it is not going to come into effect until t equals 2 and then onward. So this is what I add to this. So I have u of t minus 2. I'm going to bring in the new behavior, minus t, and then I'm going to subtract off the old behavior, minus 1. So I'm going to just write down some tips about this. Add the new, and subtract the old. Because imagine, this term is completely, this isn't even here. Up until t equals 2, this term is equal to 0. So this is what we have. We have f of t equals 1. And then time ticks on, and now it's time equals to 1, and now it's time equals 1.5, and it's still f of t equals 1. But the moment that we get to t equals 2, suddenly this u switches from 0 to 1. So now instead of 0 times that stuff, I have 1 times that stuff. And so now I have 1 plus 1 times minus t minus 1, which gives me 1 plus minus t minus 1. 1 minus 1 is 0. That minus 1 switches off the one that was there before, and minus t now comes into effect, and that's what I have. So at this stage, at t equals 2 and onward, this is what I have. And I have to do the exact same thing once I get to t equals 3. So same deal, I'm going to add switching behavior at t equals 3, that's u of t minus 3, and then turn on the new and subtract the old. So 2t minus e to the t, and then I'm going to subtract what was there before, which was minus t. Okay, we can simplify this a little bit, so I will. If you have a lot of different u functions at the end of the day, it's nice to write them in order. This here, it looks like it's looking pretty good. You could write this as minus, and then a u of t minus 2, t plus 1, it's fine. There are lots of ways to write this, but I basically want to simplify that last term here. So we have 2t plus t, and that's 3t minus e to the t, like this. Okay. And essentially, as time goes on, those different step functions switch on from left to right, and give me more pieces of that function that you know, bring things into the fold. So this here is how we would do it. Okay, so let's try to go the other way. If we want to instead write a bunch of Heaviside functions as a piecewise function, what you want to do is, I don't know, you kind of want to undo that. It is going to seem a little bit more complicated, but it's really not. You just have to think of what's happening, and again, remember what the u functions are doing. Okay, so the first thing is to make sure that they're all in order, so you know what order those things are switching on. And then if you imagine, as those things switch on, as different switches change from 0 to 1, I'm adding extra parts of the function. And the sum of all of the different ones that are on to that point are going to make up the current behavior of the function. So essentially, I have some pretty detailed instructions here, but I don't want you to memorize this. I don't want you to use this page except for maybe to introduce yourself. I want you to listen to my words and do the examples. And once you understand how those work, you'll be able to go back here and kind of understand what these directions are really referring to, okay? But essentially, you need a bunch of intervals corresponding to the intervals between each switch, and continue to add the behavior that is being turned on in each of the branches. Okay, so let's do this example right here. We have y of t equals this whole sum of different things, and I see a couple of u of t minus 4s here, so we might want to factor this out. If you wanted to, you could rewrite this as 40 sine of t plus 25 cos of t minus 2, u of t minus 2, so I see that step function right here. And then same here, I could write u of t minus 4 and then factor out the behavior attached to that. So that is going to be a, let's see, if I write a plus u here, then I don't mess up the signs. I have a minus 4t from the looks of it, this first term right here, and then plus 5 sine of t minus 4, like this. Okay, I just ran out of room there, so I needed to start another line. But now I have the different kinds of behaviors that switch on, right? I have 40 sine t at the start. At t equals 2, 25 cos of t minus 2 is going to add to that, because this chunk is equal to 0 up until t equals 2. and then at t equals 2, this flips on, and that gets added to the 40 sine of t. And then at t equals 4, this chunk gets added to both of the previous terms. Okay, so at this point, we can go forward and say, okay, we have y of t equals, and writing everything down, I have 40 sine of t, and that's true for, let's see here, it's true for all t up until 2. But at 2, something changes. I add this second piece to it. So 40 sine of t plus 25 cos of t minus 2. And that's going to be true for t between 2 and 4, because this is when the next behavior gets added. And at 4, we now have 40 sine of t plus 25 cos, right? When you're going this way, those behaviors don't shut off. Once a u turns from 0 to 1, it's on forever. So all we have to do is add up all of the contributions going across, and the last piece gets added at t equals 4, so it's minus 4t plus 5 sine of t minus 4. And that's true for t greater than or equal to 4. Really, I think it's very straightforward as long as you practice a little bit and see how it works. Okay, so this is going to be a little bit closer to something that you might see and need while doing differential equations. So I wanted to take this one step further. We might have to take the Laplace transform of one of these things, but if you're given a piecewise function, you can't take the Laplace transform of this directly. I need to see what it looks like in terms of step functions first. So convert to step functions first. And then we'll use the Laplace transform formulas that we came up with last time. So we have here that f of t equals, so using the same sort of idea, I'm going to, this is changing from piecewise to step functions. So I have to think of how that works. It's 5 to start. And then at t equals 1, something changes. So at t equals 1, I want something to turn on and I want something to turn off. The thing I want to turn on is 3t. The thing I want to turn off is the 5. So I have 5 plus u of t minus 1 is going to be either 0 or 1. At t equals 1, it changes to a 1, and now I'm multiplying by 1 a 3t minus 5. So the 5 minus 5 cancel out, and I get the 3t. So this is what I've got, but now we have to take the Laplace transform. And this goes back to the last lecture and how we approach this. So let's do that. So we're going to have to think of a couple of things here. We're going to take the Laplace of f of t, or if you like, we could call it capital F of s. And we're going to get here 5 over s. Okay, that one's easy to start with. And then we have to think of what that second part is going to be like. I need to take the Laplace transform of this piece. And if I rewrite this, I'm going to rewrite it on the line up here so I can do some good things here. I need to, if you remember, we have to have the t minus 1 matching in order to take the Laplace transform of something that involves a step function if it isn't just a step function on its own. So I need to write 3t minus 5 in terms of t minus 1. So this here, need to write in terms of t minus 1. That Laplace transform formula required the argument of the function to match the step function. The t minus 1 has to appear in that function. So that means that I need to write a t minus 1 here somehow. So let's do that. Let's do that, and we'll see what that looks like. So typically what I'll do is write this as a t minus 1, and then I got to think of how I need to change this around. So if I write a t minus 1 here, and I have a u times that, well, originally I had a 3t here, and so I want to change the constant out front, the coefficient, so that I get the 3t that I started with I'll put that right here. So see, now I have 3 times t times the u, just like here I have 3 times t times the u. But at the same time, when I have the t minus 1 here, now I have -1 times 3 times the u, which is minus 3 times the u. I started with minus 5 times the u. So I have to add in a remainder term, or actually subtract off an additional 2u to make up that difference. So this here I need a minus 2u of t minus 1 to add into the picture to make sure I get to the same equivalent thing that I started with. I kind of just did that in my head because it's hard to do much more than that other than to explain again where this came from. So the 5 and the 5, those go together, no problem. So let's look at the inside piece, and I'll show you what I did one more time. I needed this bracket, the square bracket here, in terms of t minus 1. So I wrote t minus 1 here, but then I have to correct that to make sure that I have the original square bracket. 3 times t minus 1 is 3t minus 3. I have that multiplied by u, which I need, but I have 3t minus 5 to begin with, so I need to subtract 2 more u off, and that's where this other thing comes from. But see, now I have 2 different kinds of Heaviside function forms here that I can actually take the Laplace transform of using the formulas. Okay, so given that, we are going to just making clear, right? This is all one line here. 5 plus 3u times this minus 2u, and so on. But I'm worried that this last piece looks a lot like something else. I'm going to write it in red, just because I'm going to get questions otherwise. So minus, I subtracted off 2 more u of t minus 1s. And that should get me what I need. Okay, so we're taking the Laplace transform now, and that shouldn't be too hard. Remember that for Heaviside functions, what do we need to do? We need to remember that an exponential goes with them, so we get e to the minus s, and then we multiply by the Laplace transform of this function without the shift. And that is going to be the Laplace transform of t, which is 1 over s squared. And the last piece is going to be minus 2 times the Laplace transform of u of t minus 1. That's e to the minus s over s. I'm just going to move this 5 over s down a little bit so it all looks like one line. But that's it. This is what it is. So it's necessary to keep those different Laplace transform formulas in mind and know how to use them. And remember that when you have those Heaviside functions, that matching sort of process has to be there. But in the first place, if you're given a piecewise function like that, you do have to convert first, or you have no hope of taking the Laplace transform. It's not enough to just take the Laplace transform of each piece, because then you miss that switching behavior, and your Laplace transform, you might miss out on the fact that there have to be exponentials there. All right. So, we're going to actually use these to do one last pretty big example, but it's not really going to be any different than finding differential equation solutions using Laplace transforms, like we did a couple of lectures ago. Now, it's a little bit interesting, right? Because we're talking about differential equations, where I said there's switching behavior on the right-hand side as the forcing term. And it's a little bit weird to think of a differential equation having discontinuities in it, because, I mean, you know, if you have a forcing term that's not continuous, but you need a solution that, like, it's a differential equation where we have derivatives in play. And in first year, you're told that differentiability implies continuity, and so there's a little bit of a disconnect there. It's a little bit, there's more to that story. We have the tools that we need to be able to deal with that stuff, but I want you to know what to expect, okay? What do the solutions look like? If you have some sort of a differential equation solution and the force suddenly changes all at once, there's still some properties that we can expect from the solution. So even though these differential equations might have solutions that are not differentiable at those points where the behavior switches, ultimately we require that solutions for these differential equations are differentiable on any open interval between those steps, and then even at that switched behavior, you still have continuity of the solution at those points. This is really important because if you think about it, going back to some of those examples we did with applications, maybe you are, exerting some force on a pendulum, because that's the example that I like to use a lot, because you can just see it, and you're providing some sort of force to make a swing go a certain way. You're pushing a kid on the swing or whatever. But then at a certain time, suddenly, the force that's being exerted on the kid in the swing changes. Maybe it's like, maybe there's no force suddenly, or maybe there's a sudden gust of wind that comes in and puts additional force. The continuity of the solution is really important because it guarantees one very important thing, that when that behavior occurs with the extra force, the kid doesn't suddenly teleport in place and go someplace else, right? Like, it's important to recognize that even if the force acting on the system suddenly changes, that doesn't change where the position of whatever's being modeled is. I mean, that's only for applications that are where there's like some sort of physical position to talk about. But this actually is true for any differential equations involving these objects. We want to make sure that there's continuity at those points where the force changes. Okay, and as I mentioned before, it's important that discontinuous forcing terms are written in terms of Heaviside functions so that we can actually take the Laplace transform to deal with them. So we are going to solve this differential equation. This will be our last one for the day, and we're going to find the solution to this initial value problem. Notice that it says for t greater than or equal to 0, and that's simply because when we find that Laplace transform, that throws away any data from before t equals 0, as I've talked about, and then when you take the inverse transform and come back, you get functions that are valid only from t equals 0 on. So we have 0 if t is less than pi, something switches on and we have a force of 1 between pi and 2 pi, and then back to 0 afterward. So we have y double prime plus 4y. We should probably know at this point kind of what to expect in terms of what functions we'll get that are involved here. When I see a y double prime plus 4y on the left-hand side, and I think of everything I know about homogeneous and particular solutions and that sort of thing, I'm expecting sines and coses from that, purely imaginary roots. The thing is, none of our other techniques really work on this differential equation from the non-homogeneous section because I have this discontinuous right-hand side. We have to use Laplace transforms. We're given an initial value problem as well, so we have initial conditions there, and we know that Laplace transforms work really well with that too. So, first step, convert to Heaviside functions. That's essential, so that we can actually take the Laplace. That's not hard. We have y double prime plus 4y equals, and it looks like we have 0 to start with, so I'll write 0 to start with, but then at pi, at t equals pi, I change and turn something on. So I'm going u of t minus pi, and what turns on? Oh, a 1. What turns off? Well, the 0 that was there, right? You're really just adding 1 at that point, so you can just add that function into play. And then at t equals 2 pi, I want to shut off that behavior. So I'm going to turn, if you will, on the 0 and subtract off the 1. If you're good at these things and you understand how the step functions work, you might be able to see pretty quickly that you just have to add on a u of t minus pi and subtract off a u of t minus 2 pi, or t minus 2 pi. But it's nice to practice those techniques from the last few pages. So really, at the end of the day, we have this differential equation to work with. And you can see on the right-hand side that when t equals pi and this thing turns on, I get a 1. And then at u of t minus 2 pi, this second thing turns on, I get 1 minus 1, which is 0. And so I get the 0 going to 1 going to 0. And you can see it in front of your face. Okay. All right. So for this, you remember that unlike undetermined coefficients and variation of parameters, there's no need to find YH and YP. It happens automatically when you take the Laplace transform. And solving the initial value problem happens automatically when you take Laplace transforms. So all we have to do is take the Laplace transform. And if we go across taking that Laplace transform, the Laplace of y double prime was s squared L of y, and then we go down the powers of s as we go up the initial conditions, and we get something that looks like this. Plus 4y is plus 4L of y now. And on the right, we have two simple step functions. So we have, this is e to the minus pi s over s, and the second one is minus e to the minus 2 pi s over s. We know what y of 0 and y prime of 0 are. Those are equal to 1 and 0. So this is 1, this is 0, and I'm going to rearrange, factor out L of y, and work on getting towards a solution here. So we have L of y. If I factor out the s squared plus 4, like this, that seems like a good thing. And I'm going to take this minus s over to the other side, and then I get e to the minus pi s over s minus e to the minus 2 pi s over s, and then plus s, taking this one over to the other side. All right, I can now divide by s squared plus 4. And if I do, I have L of y equals, and then I'm actually going to do something here, and I'm going to write e to the minus pi s. I'm going to take this s and write it as 1 over s, because then I can see, I'm writing into a form where I can recognize a different Laplace transform formula, the one that has e to the minus as times some function that we then have to deal with. So I'm going to divide down that s squared plus 4. That goes to all of these terms. So I think we get this. And I'll do the same thing here. So 1 over s squared plus 4. And then finally we have a plus s over s squared plus 4. Okay, so this is what we got. Unfortunately, so let's take a look at what we have here. This here is a formula that looks like it's just going to be a simple cosine function once I go backwards. This and this, so this will be a cos. Okay, these here don't look like anything right now, but it's going to be multiplied by an exponential in both cases. But in each one of those, I actually have to use partial fractions to break these down. Use partial fractions. So that's going to be our next step. Breaking those down, and I'll be able to see the different combinations of functions that hid an exponential. One mistake that some students make when they get to a situation like this is that they see an exponential, they don't write it out front, and then they try to do partial fractions using an exponential on the top, which can never work. It's just not going to, because I can't find the right sorts of combinations of functions and polynomials to match like exponentials on the top. So take the exponentials, write them out front, and then just deal with normal partial fractions at this stage of the game. So let's do that. Let's use the partial fractions. So let's use partial fractions. And it looks like it's not going to be too hard here. but we want 1 over s, and thank goodness the same partial fractions question comes up twice here, so we don't have to do it twice, but in general, you might have to do more, depending on the problem. So we want to write it like this, and it looks like we can get A for free using Heaviside cover-up. Heaviside's just like pulling more than his weight here. He's like appearing in multiple places in this problem to help us out. Real hero there. So I want to get A. I'm going to cover up the S, plug in a 0, and I get 1 over 4. That should be not too tough. And then we're going to do common denominators to figure out the rest. So 1 over s squared plus 4 is equal to a times s squared plus 4 plus bs plus c times s over s times s squared plus 4. Okay, we know what a is. We need to figure out what b and c are. Let's match up the s squareds first. So the coefficient of s squared on the left and the right, if we match powers in the numerator, the coefficient of s squared on the top is 0 on the left, and on the right it's a plus b. And that's going to force, let's see here, a, we already have, is 1/4, so that's going to make b equal to negative 1/4. Okay, and the coefficient of, let's see, the c is attached to s, and so let's look at the s terms. On the left I have 0, because I only have a 1 on the top there, so I don't have any s's or s squared, so I have a 0 and 0, but the coefficient of s is 0 on the left, and on the right, the only just s term is cs. So what's really nice here is that we do have a 0 for the c, so that kind of makes things a little bit better. But we have a little bit of work to do. A is 1/4, b is minus 1/4, and so we have to kind of write out these fractions using this. So I'm going to take what we had before and rewrite what we had. So I'm going to say, thus we get. Thus we get. We have that L of y is equal to. Now, e to the minus pi s is going to be multiplied by the result of the partial fractions. So e to the minus pi s is going to be multiplied by what we just found. So that's 1/4 over s, and then plus bs plus c. So it's going to be plus negative 1/4 s plus 0 over s squared plus 4, like this. And then we have minus the e to the minus 2 pi s. So carefully, minus e to the minus 2 pi s, and then it'll be the same thing, 1/4 over s, and then minus 1/4 s over s squared plus 4, just like that. And then the last term here is plus s over s squared plus 4. Okay, so we got a lot going on here, but I think that you can see kind of where this is going. We can take the Laplace transform inverse of all of the different pieces here to get to our answer. If you need to multiply this exponential through to see all the different pieces, that's cool. I'm going to try to read this off here and kind of move things along. So inverse transform time. So I'm taking the inverse transform of e to the minus pi s over s times 1/4. So I'm going to get 1/4, and e to the minus pi s over s is just a regular old Heaviside function. So 1/4 u of t minus pi. That's the first one. We're finished this one. Check mark. Second one, I have a minus 1/4 here. So I'm going to start with the minus 1/4. And then I have the exponential e to the minus pi s times s over s squared plus 4, right? That's this one times this one. So let's see. The e to the minus pi s, I know there's got to be a step function in there, so u of t minus pi is still going to be here. But now I have to multiply by whatever the inverse transform of s over s squared plus 4 is. S over s squared plus 4 is going to be cos of 2t. So I want to write down cos of 2, and then as I go to write down t, I remember how that formula works, because when you're going backward, you have to use that shift rule. And you have to take that 2t and shift the t to match the u. That's from the last lecture. That's from using that formula. So I get 2 times t minus pi instead of just a 2t. Okay, so that's how that works. If you need to review how that works, don't hesitate. Go back, watch that last lecture, make sure you master that, and then come back and be like, I get it. Okay, let's keep going. The second one. So we've now done this, and now we want to do the next one. So we have minus a quarter, but this time it's u of t minus 2 pi, and that's this term right here. So we've done that. That's no problem. That's just a basic Heaviside function as well. But now we have to multiply that by this term here. I have a minus a quarter. That makes plus a quarter. I have a u of t minus 2 pi now, looking at that exponential. And this time I'm going to have cos of still 2t, but now I have to shift it to be t minus 2 pi to match. Finally, I have to take the Laplace inverse of that last function, which is nothing more than a cos of 2t from the looks of it. Now, one thing I want you to do at the end of the day is to learn to collect all of the like step functions, because that makes it a lot easier for us to grade things, and it makes your solution look a lot more organized. So collect like step functions. That means write all of the u of t minus pi's as a single term. Write all of the u of t minus 2 pi's as a single term. And we get y equals, and then if I write u of t minus pi, you know what? Maybe I will write even the thing that was without any step function first, because that represents the behavior that's in play right from the start. So we have cos of 2t, and then at t equals pi, this behavior turns on. 1/4, and then minus 1/4 cos of t minus pi. And then I could do the same thing. I'm going to write this on a new line because I'm running out of room. This is the same thing as t minus 2 pi. And then at 2 pi, I have minus a quarter. And then I add a quarter cos of t minus 2 pi. This is what your solution looks like. But I want to make one last observation here, and it has to do with, let's see, the cos of 2, oh, I didn't write that down right, because it's cos of 2 times t minus 2 pi. So I almost missed that. Cos of 2 times t minus 2 pi, cos of 2 times t minus 2 pi. I'm just going to rewrite this because I screwed this up. That was just a copying error. So cos of, we had 2 times t minus pi here, and cos of 2 times t minus 2 pi right there. I caught myself. All right, so yeah, the last observation I wanted to make is this one right here. If you wrote your solution like this, I'd be super pleased you'd get full marks. Don't worry about it. But on the side, I'm going to note here that since the cosine function, cos of 2t, has a period of, and if you remember, the period of a cosine or sine function is 2 pi over the number in front of the t here, so that's going to be pi. Since cos of 2t has a period of pi, it happens that, for this example, cos of 2t is equal to the cos of 2t minus pi, which is equal to the cos of 2t minus 2 pi. And so what's really nice is that I can actually rewrite these so that they're all just cos of 2t. That's very special for this example. That's not something you can do in general, but it's something that we can observe here. And it's neat because then I can talk about something interesting. So this gives us 1/4 minus 1/4 cos of 2t. And then I can write this as u of t, 2t minus 2 pi, and then we get minus 1/4 plus 1/4 cos of 2t. And if we look at this answer, it's pretty cool. We had a force in this differential equation example that turned on at t equals pi and turned back off at t equals 2 pi. And my solution kind of reflects that. I have a particular behavior that's happening, cos of 2t, up until pi when something switches on. I can see it's 1/4 minus 1/4 cos 2t. And that's going to be added to the cos of 2t to begin with. And then at t equals 2 pi, those very same behaviors that were introduced at pi shut off. It's exactly the opposite, minus 1/4 plus 1/4 of cos of 2t. And so you get back just the cos of 2t after t equals 2 pi. So essentially you have a cos of 2t that's doing its thing, and then at pi, you get a different sort of behavior that's a different oscillation, and then as soon as that turns off, it goes back to what it was doing before. And it does so in a smooth manner, a continuous manner. So yeah, it's kind of involved. There are a lot of different steps there, and you got to remember how to do things like partial fractions when they come up, and you got to remember the shift rules when you take inverse transforms, and you have to start with converting a piecewise function into Heaviside functions, and so there's a lot to this. But it follows the same flow as everything we've done. This is another example of a differential equation with a discontinuous, this time with a discontinuous right-hand side, but another one where we've used Laplace transforms to do things. And we didn't have to apply initial conditions at the end of the day because it's done in the process. So that's pretty much it. We're going to be moving on to one last topic in discontinuous forcing terms, and we will have to use Laplace transforms for that too. It has one of my favorite derivations of the entire semester though, so it's a pretty exciting concept what's coming up. So I look forward to doing that one, and I hope you are too. I will see you then. For now, take care of yourselves.